Right. Good afternoon, guys. Um, I guess there's a lot of people. 1 second. Hi. Sorry for the technical difficulty. Okay. I guess a lot of people have not joined. So what we'll do is, um, I had promised that I'll show you the video, which for the ceiling, how it was placed. What I'm going to do is I'm going to run through it, just show the two videos which I have, and if there is any questions right now, we can answer that, or probably what we'll do is we'll continue with the workshop with Sujay. And in the end of today's lecture, we can have a cumulative discussion of what Sujay has taught today in the workshop, and or any doubts that you had of the yesterday's workshop. So quickly, I'm going to share my screen. Um, all right. So 1 second. There you go. It's a little fast, so I'm just going to try to rerun it so that you can see it again and again. So right now what you see is all the pieces which are kept on the floor. Um, and they're tying it with these hooks. So one after the other, you can see how they are doing it. So once this was done already on the floor, it became very easy for us then to take it further. So now let me take you to the other video. This is a fun video. So again, I'm just going to pause this here. So what you can see is once assembled on the ground, section by section, we rolled it as a carpet, literally as a carpet. And then we started taking it on top. There you go. You can see literally how it looks like a carpet. And from one point to the other, because the other pieces are already been installed, so each piece is getting attached. So one after the other, all these pieces are going to get attached. And yes, we are in India, so we have so many workers helping. So actually, there are three cooks there who are actually helping, um, just to support and just to keep it. And so yes, there is a manual problem which happened. And then again, there's a much larger video which I'm going to run through. So there's a very first section which was getting installed, and you can see that what we are doing is we are just putting these GI wires and holding it at the hooks that we had placed at every 3 feet intervals. 3 feet is roughly around a meter, 900 to a meter. So what happens is then it becomes easier to figure out like how the shape goes. And if you see on the right hand side, um, we have not stuck it to the wall yet. We've just left it out, because what happens in the next section, we don't really know. So once this next section comes in, it becomes easier for us then to put the edge pieces there. And I'm just running through it, and you can see how it changed, and how we are wrapping the entire uh, duct area. So again, because it wasn't looking nice, so we pulled it out and we're putting it back one by one. So again, there's a longer video, but I'm gonna just fast forward it. Uh, And you can see the other sections which are rolled down on the floor. Now, the first section is almost ready. What we are going to do is now take the second section and start attaching it. So the entire area was not stitched together. So we put it in section because it's easy to handle and manage. So that was that. So yes, so this is something which I wanted to share with you guys. And what I'm going to do is right now, I'll ask Sujay to join in and ask him to start with his workshop today.
Hi. Can you all hear me? Am I audible? All right. Sounds good. So let me start to share my screen. Yeah. So first things I have, which is a drive link. Yeah. Okay, quickly, I have shared a couple of notes out here about the lecture that I'll be taking and small workflow and tutorials for the Robot Studio that will be covering. We won't be covering a whole lot of it. We don't need to learn a whole lot of Robot Studio, but just to understand the interface, because some things are good to know, especially if you have to visualize something in about any collision related aspects of a robot while we are doing it in Grasshopper. Apart from that, I've shared some files within this thing and also a robot model. This we'll look at, if time permits, we'll look at it today or else tomorrow, but how to configure our robot for the robots plugin. Yes, that was the two things that I've shared. Feel free to look through it as I show it, or as I show, or you can look at it later. Not an issue. But yes, we will be starting with a quick introductory presentation on of what robotic fabrication is, of how I understand robotic fabrication, what are the possibilities, a little bit of the history, and a whole lot of what we can work with. It will start with a little bit of theory, history, and a couple of things that Shashank already covered yesterday with its role within digital fabrication. And then we'll go down to the nuts and bolts, a little more technical into the details. And this is a continuous evolution of work. So you can see it is a very long presentation of right now. It's up to 96 slides. I would hopefully want to run over the whole lot of things and leave a little bit of the theory and the history aside, and hopefully get down to the nuts and bolts faster, so that we can, in the short time, we can start coding within Grasshopper the scripts and see how we can start it. So without much. All right. Okay. All right, quickly, introduction to robotic fabrication. Okay, so this is where we are picking up our tools from, the assembly line. This is what the robot, when it was developed, was meant to be retrofitted out. This is what its ideal environment is. This is the ideal habitat of the robot. But given the recent developments within technology, within the kind of software that has been developed, and the general enthusiasm of shifting design dialogue towards a more technological front, we have co-opted this technology. We've adopted this technology from the assembly line into our field, which is a more bespoke field, rather, if you say. We are not invested in manufacturing hundreds of products. We are mostly invested in manufacturing one specific kind of product for a specific purpose. So it's rather functional, rather bespoke, rather discrete. But adopting this technology was not easy because it wasn't designed for that. So it took a couple of tries, took a couple of evolutions before we actually got into the place. And how we got to that, we'll see that soon in this presentation. Quickly, this is a lot of what Shashank covered yesterday about what is digital fabrication. It is data to production. So we use CAD tools. We convert all those information. All the information is encoded within the data and within the design process, and all that data is then translated into the production and finally the output. There is no loss of information that has happened during the entire process. So this is how the digital fabrication process works. You have it's software, CAD to CAM to production. This thing. So yes, so a lot of this is built on the back of a lot of technology, particularly the CAD format, the computer-aided engineering format, on a lot of CAM softwares, which the different varieties of CAM softwares and CAM formats include are being adopted in different machines, such as the milling machines, the 3D printers, and including the robotic arm. So this transition from data from one type into the other type is quite instrumental in how digital fabrication works. And this workflow is essentially what we'll be looking at. And one of the good advantages of this workflow is that we can intervene at any stage, and we can tweak and change the design as possible, and the workflow can adopt to the process. And we also tend to have feedback loops within this thing. And that is very important, because since we are not in the business of prototyping a lot, like how automotive production works, we have to rely on some sort of feedback which would directly get into which would directly inform the design process, and the next subsequent iterations could involve the changes that are required to it. So within the digital fabrication process, we are looking at change of data from one type to the other, and we are looking at how a feedback loop can exist. So these are the key aspects of how digital fabrication works, and this is how we look at it. So within the whole gambit of digital fabrication, we have a smaller field called robotic fabrication. And robotic fabrication is nothing. We use actually a lot of it. This is kind of deceptive, and how I'll show you. But robotic fabrication is a smaller field within the whole gambit of this thing, and we shall see how that works. Within this robotic fabrication, we are mainly focusing on the robotic arm, the 6-axis anthropomorphic arm, and how we can use the robot to develop workflows for production, as we'll see. Now, I think Shashank covered a lot of this yesterday. How we classify digital fabrication by technique: we have additive, we have subtractive, and we have robotic manipulation. Additive is 3D printing, subtractive is milling and or laser cutting, and robotic manipulation involves a couple of processes, one of which can be pick and place, that we'll look at. Yeah. But the definition over time, at least of lately, has expanded to include both the processes to create a new hybrid process. We also have assembly type robotics, which does not essentially produce, but it is putting things together. As also we have these bespoke robotics, which does not really look at which is robots that are designed for a specific purpose. It cannot go beyond a certain role that it's designed to do. So that is a new and emerging field that we'll be looking at. So subtractive, the advantages is that you can mill it up to a final product. It is much more defined. The starting material is harder. You have a properly defined material such as wood and stone and metal that we can use. Whereas additive, you have some advantages such as you use very little material, it's economical, and such advantages, as we know, exist. But now this is how I would like to describe the whole field of robotic fabrication and or digital fabrication. That we are breaking down it, we are deconstructing the process into its components, namely the robot or the manipulator, onto which we mount the tool, and which is being used on a certain type of material. And a permutation combination of all of this can define one or the other machine that we use for our digital fabrication processes. Let us see how we can do that. Now, we have this whole array of robots. Now, the Cartesian robot is what we've commonly seen in 3D printers in the CNC mill. So that is one kind of manipulator that we are looking at. Apart from that, there are these numerous robots that we may or may not see commonly. The cylindrical robot is something that we look at as large-scale cranes that we see on construction site. And now here we are going to look at the articulated robot. We also see large-scale delta robots or parallel robots in the field. And the tool could be anything. These are the two most commonly used tools in our fields: the spindle or the mill for subtractive manufacturing, and the nozzle or the extruder for additive manufacturing that we use. So either of this can be mounted. And then we have a whole array of materials. This is seemingly endless. Every day we see ourselves experimenting and developing new materials. This is by no means the most comprehensive list, and I'm sure this is going to change within the next couple of years as well. So looking at breaking down additive manufacturing by the rules that we just defined. So we have the Cartesian robot onto which we are mounting an extruder or a nozzle, and we can either use a polymer-based material and or a cementitious material to create some sort of an additive manufacturing robot. So we've used a lot. So a lot of such additive manufacturing research is going on. Somehow you can see the articulated robot or the robotic arm also contributing to the additive manufacturing processes. So that this is one way we can use all these technologies that are being evolved. And then there are other kinds of additive manufacturing, which is robot independent. So here you have a spherical robot onto which you're having another extruder attached to it, and we are having concrete printing happening. So this is Apiscore, a 3D printing house company, which has developed this sort of a model to use the technology. Okay, here we see binder jetting, which is using the binder jetting process is being used. A Cartesian robot is being used, and sand is being used. So you have the whole a different permutation combination of the manipulator tool and material being used out here. Okay, this is also interesting. You have a spherical robot. This is actually a boom arm. Onto the end, they mounted a robotic arm. And then this is sort of an FDM process, and they're using foam. It's been developed by Dr. Stephen Keating at MIT. So again, a different permutation combination that we can see out here. See, and the common forms of subtractive manufacturing we see, we have the Cartesian robot. We use the spindle, and we use materials such as wood, or we use stone, or any form of hardened material that we can use for the manufacturing process. So you see the CNC router, which is the most commonly widely used, which is one of the most commonly used tool within our fields. Very versatile, and which can be used to develop a whole lot of, which can be used to mill a whole lot of materials that we see. Primarily used for a lot of sheet wood, plywood, etc. The tools within that we use for on the CNC could be two different types: water-cooled spindle, air-cooled spindle. Both have their advantages. The water-cooled is slightly better, faster, and can involve a lot more power and just last a little longer, and it's cooled faster as compared to the air-cooled. But yes, it needs a little less infrastructure to mount the air-cooled one than the water-cooled one. So yes, all those advantages, disadvantages exist between these tools that we see. This is one of the processes that we can use, optimizing the use of material in the right places and removing the additional material, and then trying to reinforce some aspects of the form that we can see out here. So again, another kind of exploratory process of how subtractive manufacturing can be used. Finally, we are coming down to our main concept, the robotic manipulation aspect of what we're looking at. So now we see the robotic arm, onto which, again, this by itself is a tool it is probably quite a useless tool until you mount the right. It's probably a useless robot, useless manipulator until you mount the right tool onto it. And each tool, and depending on the job that you want to do, there is a whole variety of tools that are available or can be developed for this process. So here we see a modified bandsaw being used to cut the wood along the curve. So this is one custom made tool that can be mounted onto it. Now, how did we get to this stage? A little bit, let's dwell into the history of the whole robotic arm and how it was developed over years. We go back to 1959, where we see the first industrial iteration of this robot being developed. And it is a robotic arm called Unimate. And it was developed with the sole purpose of being implemented in the industrial setup. Yeah, we'll just quickly see a small clip of this. So this is an iteration of the circular robot, the spherical robot. It goes along the whole circular space, the polar axis, as well as the X and Y axis, X and Z axis.
First opposite the same movement of the new ones.
All right, but one thing to notice is yes, I think there's a question out here. First robot did the same movement. All right, okay, sorry. 1 second. Yeah. But the fact that trying to mimic the arm or the human body was not the first. This was not the first time it has happened. Throughout history, there has been attempts to try to replicate natural movements and through some sort of technology. It started out as experiments, and later on some sort of trade show gimmicks. Of the idea evolving until it came down to our industrial listing. So one thing to notice is that this idea did not come primarily through scientific discovery, but it came through the arts. It came through fiction. It came through storytelling and different forms of storytelling, fiction, etc. All the arts were the one that developed the idea of such a automaton or a robotic arm or the term robot by itself. And over time, we see this idea taking shape. And once technology catches up to the idea that was developed, that is when we see the whole field of robotics take off completely. And the field of robotics, while it takes off and while the first iterations of the arm is being developed, we see two fields that are being developed parallelly. One is the field of computer science, and the other is the field of artificial intelligence. So these three fields almost are codependent on each other, and any evolution you see in one field contributes to the other. So computer science, robotics, and artificial intelligence are the three fields that go in hand. As soon as computer science develops, all the ideas can get translated, and then you see this evolution happening. So while the first iterations of the robot, it basically does the same, near about the same movements as you see today, but the kind of precision, the kind of sensor-based feedback, all of those things did not happen then, and that And over time, these ideas were developed further. And as technology advanced, we see more and more sensitive instruments being added to the robot until it becomes a fully functional, sensitive manipulator that we see in our labs today. So over time, you see a lot of contributions by various research lab, which developed, and you see the final iteration of the robot that we see. And it's around 2007 we see for the tools that helped us helped bring the robot out of the assembly line and into the design studio. We see Grasshopper being developed, and then we see KUKA PRC being developed by Johannes and Sigrid Bell Cochran. So this once that abstraction happens, where you have the robotic language, the KRL language of the KUKA being abstracted into a plugin that can be read by our softwares, then the level of ideation has exploded. And then you see a lot of other plugins and other tools being developed, which makes it far simpler. So I think it takes the first step. The first step is what it took before the whole field of robotic fabrication began to take off. And so this is KUKA PRC. It's a fantastic plugin. It just simplifies the whole field. No more complex coding, no more this thing. So speaking about the earlier concept about CAD and CAM being integrated into a single workflow, this is the KUKA PRC does the exact same thing, where you have the design CAD software, and then this plugin converts the design CAD language into a CAM language, and then finally we can take it to the real world for fabrication. So a lot of good tutorials were developed by Carl Singlein. Of lately, he's put his videos on private. I don't know what happened, but yes, it's bad news for us. Otherwise, this is the go-to channel for all information regarding robotics. I'll try to speak to Carl. I don't know why he's shut his YouTube channel off, but let's hope he will probably make it open again for us. It's a good learning source, but most recommended. Yes. Now getting down deeper into the robotic arm. Firstly, mainly, let's go through the types and classification that we see. Within the field of robotics can be looked at from different angles. The architect, the designers will look at it from a specific lens. The engineers look at it from a specific lens. So based on that, there are different ways of classification that we can look at. And if you were to ask an engineer how he would classify robotics, this is probably one of the methods that, or a robotics engineer, roboticist, how they would classify the field of robotics and where does the robotic arm position itself in their field. Then this is one of the ways that they would classify. All classifications are valid, but we are not invested in the whole world of robotics. We are probably invested in the top row of stationary robots. That is one of the that is mainly the field that helps us. And then somewhere, some of the wheeled robots and some of the flying robots also help us, namely drones and rovers are also part of our tools and part of our arsenal that we can use to get data for, or to generate a lot of data-driven workflows. So, but as I said, this is one of the robots that this is the field, this is the area or one that we use. We use a Cartesian robot for our 3D printers, for our CNC robots. We use the cylindrical robots and cranes and some of our gantries, etc. The spherical robot is, we use the spherical robot for cranes, and cylindrical robot, I'm sure it's some variant is being used somewhere. One of our interesting robots that we have is the SCARA robot. It's quite it has dual polar axis. It has one that rotates around itself and the second arm that rotates around this thing, and then extruder and the third arm that goes vertically up and down. This thing that has a lot more interesting possibilities in terms of developing. And then lastly, you have the articulated robot. This whole of this table, the first, second, third, the first 5 rows all come under one section of it follows a principle of kinematics called serial kinematics, wherein you can see each arm is linked to the other at the end. So it is connected by the first arm is connected to the second arm at the end, and then the third arm is connected at the other end. So all the links are connected end to end and in a series. So that's why it's called serial kinematics. We have one other type of robot called the parallel robot, which we do see in our this thing. It has all the links are connected parallelly to each other. So you see this, the specific example that we look at is the Delta robot, which is used in some 3D printers. And but one of the advantages of the Delta robot that we'll see is that it can scale up to great heights. Actually. Yeah. So here you have just running through examples of partition. So you have the CNC, we have the cylindrical robot, we have the spherical robot, which is a Unimet, and we have a SCARA robot that is available to us. This is the Delta robot. It's quite interesting way to do, but there are 3D printers that uses, it is very fast compared to the Cartesian robot in terms of its movements, but there are some limitations to this robot as well. But yes, as I said, it can scale up quite massive. And one of the disadvantages, I think, is that it cannot carry a lot of load onto it. But other than that, if you want to print full-size houses, then yes, this is one of the tools that you can look at. Finally, we are reaching the robot that we will be exploring within this session, namely the articulated robot or the robotic arm. 3 of the most popular brands that we normally use are the UR, the KUKA, and the ABB. Not to mention that there are other brands such as the Fanuc and Yashikawa and other such brands. Also great robots, but I think one of the reason they are not heard of is that I think is because they haven't, the technology has been abstracted into the same kind of plugins that we use in our field. I suppose there are a few, but they aren't very popular outside outside the fabrication space. So outside the industrial space, sorry. And yes, so I think once it's a matter of time before those robots are also co-opted into our field. So hopefully we'll see that in the future. Okay. As I mentioned up to the reason about why some of these, about the advantages of this serial kinematics is that it can have a higher payload, there is a high degree of freedom, and it has a larger workspace. But one of the disadvantages that we will see is that over time, the errors add up. There is always lesser accuracy in this robot as compared to a parallel robot. Any small error that you will generate in the first link will extrapolate to a larger error by the time it reaches the final link or the final arm at the end, and down to the tooltip, the error gets extrapolated to a high degree. So that is one disadvantage. So it is always, whenever we are purchasing a robot, a lot of the robots that have been used in the design studios have been second-hand robots that come down from, are handed down to us from the automotive industry or aeronautical industry. One of the tests that they check for to ensure that the robot is still within limits of accuracy is something called repeatability. The robot has to touch a single point maybe 1,000 times, maybe 10,000 times. Out of this 10,000 times, maybe there will be a slight deviation of 1 mm, 2 mm. So for our field, it is not a big problem, but for the field of machining, that is a big problem. So those robots are then discarded, and we can use those robots. So that the repeatability, the error of repeatability up to 1 mm is fine for us. It is not a big error that we would see in our fabrication processes, but definitely a no-no in any industrial processes. So yeah. Okay, and when you look at the Delta robot, it doesn't have a higher payload, but it is very fast in its movements and it has a high level of accuracy. But yes, it does have smaller workspaces, and if you want to build a larger robot, you'll have to build a larger crane, a larger setup, and that will be essential before you can build this. You can use this robot. Okay, now getting back to the 6-axis robotic arm, this has these are the 6 axes. First is the base axis that you'll see. Then you have the second axis, which is the entire arm. If I was to try to mimic the human motions, the first axis is where the whole body can rotate. The second axis is where your arm can rotate. The third axis is where your elbow can rotate. And then you have the fourth axis, which is the forearm that can rotate. And then you have the wrist, and finally the fingers. So those are the 6 degrees of freedom that you can see out here. Okay. Oh, 1 second. There is. Okay. All right, Diego, we'll have a look at this. 1 second. In this thing. So each robot has a specific payload that we're looking at, has a reach. And again, you can see the repeatability out there, which is the ideal repeatability that you need to be looking at in a lot of the robots, for a lot of the newer robots. And it also, again, it's a heavier robot. So each has its own specifications, and depending on its size, it's certain limitations as well. The smaller 6-axis robots are far accurate and far sensitive than the larger robots. The bigger they are, then the same problem that you will face. This thing. Okay, looking at the setup of the robot, this is how this current setup is, where you have the main manipulator, this thing which is connected to the main controller, which has the system module and the drive module, which both of this thing controls the joint positions and sends the converts the G code, the machine code or the rapid code, into a series of movements, a series of electrical signals, which is then converted into movements in the servo motor, which allow you to transition from the code to a point in space. So that is what the drive module does. And then apart from that, you have the teach pendant or the flex pendant, which is the human machine interface that you have. And then you will have your external power supply. You might have an external separate axis or a separate setup, like a rotary table or any other gantry setup that can move the robot. That all those things are also connected to the robot. And lastly, you have the computer onto which you are going to send the information from onto the controller, which then translates it into the motion. So this is the diagram of how the architecture of the robotic lab is set up. The ABB uses a controller called the IRC5 controller, which is the latest, the later model, the most recent model, I would say, of the controller. It is the better controller. Earlier versions use the SC4 Plus on the SC4, and they have not been fully adopted into our the Grasshopper Rhino plugin workflow, although they can be used via the native software such as Robot Studio. But I think the whole shift towards a smarter and easily available setup is what we are seeing. So dependent that is being used by the recent models. Once you will open up the controller, these are the portions that you'll see. You can see this is the main. This is the brain. This is how the brain of the controller looks like. You have the main power switch. You have an emergency stop button. Below that, you will see motors on. It is a feedback which ensures that the motor is fully functional, the robot is good to go. Below that, you will have another small key which changes from manual to automatic mode. And then below that, you'll see two ports. One is a service port, which will allow you to connect the controller to your laptop if you want to directly send information from the to your to the robot. And the other is the connection to the flex pendant, which will then interface you to control it manually. So again, this is how the flex pendant looks like. You can have a look at it. If you ever had a chance to see it, it's just basically like a remote control. You have the screen, the touchpad, then you will have the joystick and a couple of buttons which can be programmed to do specific tasks. You have your main emergency stop. You have a port for the USB to feed in the program manually. And then on the bottom, you'll have a dead man switch, which is a very important tool if you're handling the robot manually. In case something happens to the operator, the robot is immediately shut down by the when you let go of the switch. Looking at the different modes that are available for us, you have the manual mode, you have the manual 100% mode, and you have the automatic mode. Automatic mode is completely hands-free. As it mentions, you directly send in your command, your codes, your G code via your computer and or the network that you might have, and it will run continuously without any human intervention or supervision. Manual mode, you will need to hold run to run the robot, but it can be jogged at a certain speed. And the program speed, the speed that you feed in the program is going to be followed religiously. There will not be any of this thing. So manual 100% mode, you'll have to, the program speed that is specified is followed. In manual mode, you can, if you program the robot to run at a specific speed, you can change it through the flex pendant as well. And that is something that is most of what we do, because sometimes in our production, since it is a bespoke kind of production, there aren't a lot of iterations we are running, and we will be calibrating, we will be sending in a lot of points through. It is best if we have more control and you run at a less than optimal operating speed. Okay, so this is one of the important concepts that we need to clear up, is the coordinate system or the frames that we are working with. There are multiple frames that we work with, and they can be connected to each other, and most of them are similar to each other. Some of them can be tweaked to our interest, and one particular frame is slightly off. So we have the main global coordinate system, or the world XY. That is the universal coordinate system that is around us. The second coordinate system that you will see is the machine coordinate system, or the robot coordinate system. That is the coordinate system that is positioned at the base of the robot, and it is programmed at the base of the robot. The third coordinate system that you might come across is the work object coordinate system, or the workpiece coordinate system. This can be changed by the user to wherever he positions the workpiece. Multiple work coordinate system can also be developed. So you have one work object with a specific coordinate system, and then can be translated to a different frame, and that can have a different coordinate system. And there could be a direct translation between these coordinate systems, so that you pick the object and you place it to the corresponding coordinate on the other coordinate system. That is also possible. And the last coordinate system that you have is the tool coordinate system, or the TCS. Now, in all the coordinate systems, you have the z-axis on the facing upwards, but in the tool coordinate system, it is facing outward. It is facing outward on the last axis that you have. On the 6th axis, it is facing straight outward. So this translation is something that you will need to get used to a little bit. So when you are placing the tool downwards onto the work object, your both the Z coordinates are actually meeting each other. That is the best way to understand how the coordinate systems work. Yes, this is the broader definition that I just clarified. And yes, so again, the TCS is at the end of the TCP. If you're having, okay, yes, if you're having a single robot, then the global coordinate system and the machine coordinate system will be the global system. Then that is where they both are different, and that is how their relationship is important, because all the robots have to be calibrated to one kind of coordinate system so that all the files and the points can be translated between the robots by itself. Yeah. Again, so this is a native tool that we use to operate the ABB robot, that is the robot studio. This is the kind of interface of it. We will go through it in later in greater detail in the next presentation that is going to start sometime. That we'll see. I think there is a small video that I had set up. So just running through. Yeah. Okay, this is the full screen that we have. So this is basically the interface. You have an empty space, and there you can select the robot. Also, this is a slightly older, this is a video of a slightly older model or older version of Robot Studio. I think it's 5.5 right now. We are on 7, I think. Yes, so that is interesting. So I think we'll revisit this video in the next half of the presentation when we start up Robot Studio, and then we can see how we can look at it. Yes. The other thing that we need to look at is jogging, where we need to understand the kind of different motions that are available to us. The first type of jogging that we know of is our ability to isolate each and every axis and to move the axis independently. So we can move the axes 1, 2, 3, or 4, 5, 6 independently. Then you have another mode called linear mode, and then you have a reorient mode, both of which I'll be covering in the demo of Robot Studio. And that is something that we can look at that. TCP definition. This is one of the most important things that we need to define. There are a few things that we need to that are quite important to define. First is the robot's coordinate system. Then you need the tool coordinate system, the TCP or the tool coordinate point. Then you need to define the work object, and what are the last? Yes, I think these 3 things are, and then finally is the path plan that is involved. These 4 things really essentially are required for you to develop the G code for you to run the robot. So how do you define the TCP? You fix a point in space, and then you try to collect you try to reach this point to 3 or 4 different tries to the same point. You do that to try to reduce the error between the definition of the point. And once you have that, you can have a fairly accurate point. We'll try to demonstrate this in the Robot Studio tutorial that we are going to see. I think this is okay, this is creating a small video. Oh yeah, this is so one of the advantages of the flex pendant is that you can make small programs within it by going through the program mode. I think I will just rewind a little bit behind. There is a program editor in Robot Studio, which allows you to make small programs, and you can teach the robot to move to specific positions and create a small program by that process. It is slightly tedious, and it can be done for small for pick and place projects where the location of the pick and the location of the place is more or less similar. You cannot use this kind of programming using flex pendant to develop large milling projects. That is unfeasible because there you have to deal with a lot more points than what is possible to do via the flex pendant. So we shall go through this video, but more than that, I think it is important for us to know how to develop it via the plugins, because we'll be dealing with a few thousand points, and this is not the way to go about it. But it's important to know if you want to tweak small things like add a small definition of a home position, then that can be done via while you've loaded the code, and then you can define a small home position, or you can for it to go at the end of the project, end of the milling process. So again, this is something that we can look at. Oops. One second, was that a different video? Oh, no. Okay. Yeah. One of the things that we look at is the different types of motions that we have. There are three different types of motions. One is the linear motion, then you have point-to-point motion, and then you have a circular motion. Linear motion is between 2 points. You have the straightest path that you go. That is the linear. That would be the linear motion. Point-to-point is where you define waypoints, and it touches each point and goes through. So that is point-to-point motion. Each and every point along the path is defined. Circular motion is, there are two ways to look at circular motion. KUKA defines it as a curve between 2 points, but there is something called move J in ABB, which is a joint motion. It is the fastest path between 2 points based on joint movements rather than a linear motion. So if you look at the PTP, the point-to-point motion in KUKA, it is very similar to movement J. Sorry, I think I was mistaken the previous one. The circular motion is not movement J. The point-to-point motion is movement J. It goes between 2 points, but it goes fastest. It goes really fast between 2 points, and it is defined by the joint axes rather than the linear motion. The move J tends to be slightly faster because it is an optimized motion based on the minimal number of motor movements, whereas move L tends to be faster because certain the motor will have to move more or less based on the path, which is a straight line. So okay, circular motion is something that has a waypoint defined, an auxiliary point, and it goes along the curve in that manner. Yes, that is the circular motion is not a move J. We also now have a 7-axis robot. This is the KUKA EVA, but it is also one of the later models of the robot. It has a lot more sensors into it. It has force feedback, so if the robot were to hit across an obstacle, it will realize it and stop. You can define certain pressure onto it, whether if you have to use a nail gun or something like that. There is some pressure has to be applied. You can define the kind of force by which it has to use the tool. So it has different sensors to train itself manually. So it is one of the smarter robots that are available to us at this point. The UR robot is also very similar to this. Similar features, not quite so much as the KUKA EVA, but close. Okay, that was the robot that we looked at. Now we're looking at tools, and there are a lot of tools that can be developed. It's only limited by the task that you are trying to accomplish, and how you're trying to, and the path that you're using to develop. So You have grippers. You have different types of grippers that you can use. Vacuum grippers. You can have pneumatic grippers, precision grippers. So a whole lot of different grippers that can be programmed to use. Used mainly for pick and place, but that is quite interesting in its own right. Then you have the hot wire cutter, which is used to cut foam, shape foam. That's quite available out there. You have different types of extruders. This is the PET extruders that can be developed. You have a heating clamp, and then you have a NEMA motor with an auger screw in it, which pushes the material down into it and extrudes it via the nozzle at the end. So again, a commonly used tool mounted on the robot. You have cementitious mixture extruder. Here you can add clay or concrete and things like that, and that can be extruded by a screw type um, piston, which pushes the material down to the nozzle. That is there. You can also have a different type of extruder with a um, cavity pump or a positive displacement pump. Or a lot of the newer concrete printers use this type of pump. So the extruder tends to be really minimal. It's just a nozzle. The pump does the bulk of the work from the outside. So there's not a lot of technical, there's not a lot of electronics that need to be mounted onto the extruder. That's a good thing. And it can be switched on and off from the outside without any issues. Yeah, this is a prototype for a concrete extruder. You can add in a lot of weaving tools. There is robotic weaving. You can sewing, weaving, different types of things that can be done with wires. So yes, different tools are available for that, and it's only limited by the kind of by your imagination of what task you want to accomplish to that. Let's run through a few interesting projects that you will see which have been built using the robotic arms and other robotic systems. This is the Stuttgart Pavilion, the ICD Stuttgart Pavilion. This is developed interestingly. Then you have the wood chip barn developed at AA. A lot of these projects have been developed at educational institutions, and so that because a lot of research are being conducted by them. Here you see another. This is actually a form machine. This is quite an interesting project developed at ETH, where you have a smart dynamic casting that is being happening. Concrete is being extruded. Concrete is being poured and cast using this form, which can be moved to define the shape of the column. Here you have the different type of extrusion. So yes, the tools, and here there is another issue that they're not using a form book essentially. So again, quite unique by itself how they're using the project, how they're using the robotic arm. I think a lot of what is interesting is the project is standing on the robot here is just mainly a tool of how to achieve the idea, and how they achieved it basically through the thing. Here you see a cable board being used to print this thing. This is quite challenging, I would say, but yes, they've done a good job at it. Quite a large space to print in. And then the robots can get as complicated as possible. You can mount it on a lot of things. Again, quite complex by itself, but yes, this is something very exciting to look at. Yeah, I'm just covering a lot of other things that I find interesting. This is a lot of collaborative robotics that happens. You have the drone happening. You have the drone which is feeding it into the robotic arm at the ends, the cable, and then the whole pavilion is woven collaboratively by both the drone and the rover. Yeah. Now, one of the interesting and the most emerging fields is something that I'm quite fascinated with is the role of bespoke robotics. Now, this is how I'm thinking where this fits in. So we have a lot of we are started to use a robotic arm, but we need to know that this technology has come down, it's been handed down to us. It's been passed through um, the automotive industry, it's been passed to the aeronautical industry, and finally it's come down to us in our design fields. So bespoke robotics looks at it the other way, where we are looking at problems that have been facing our industry, and we are developing problem specific robots for our industry, namely design and construction. So what are the problems and what are the challenges that we are facing, and how best can we develop solutions for them? So that is the definition, and that is how I would define the role of bespoke robotics, rather than adapting the robotic arm which was designed for a specific rule. And yes, while it has been adopted within this industry quite successfully, yes, it came with a specific purpose, and it took some time before that adoption was fully materialized. But now, what if we can look at our problems, and we can develop the technology that is essential for our industry to function? This is, I think, where the whole role of bespoke robotics come in. So this is, I think, Scaled Robotics and Doxel, they have a rover which scans new construction sites and then provides feedback on the work processes and etc. This is one of my favorite projects. This is a robot developed at, I think, ICD, yes, Maria Yablonina, and she's made this wall climbing robot which helps in weaving the fibers to create different shapes and forms, etc. This is a great project. Similarly, there's another weaving robot which climbs onto fabrics to create canopies, which is being developed. Again, this is quite an emerging field. A lot of possibilities can be done, and a lot of interesting challenges can be addressed. A lot of interesting problems and challenges can be addressed through this field. Yeah. Upcoming research, what we'd hopefully see in the next few years. I think it's there. This census presentation has been a year or something old since then. It has been out there about how to integrate mixed reality with the field of robotics, and how we can visualize some of those concepts and use them to inform the fabrication process with a lot more information, and get better results, and build and or fabricate more complicated forms and other things. How can we integrate AI with robotics? This, I think, is a great idea. What if robots could think? As I said earlier, AI and robotics are the fields that go in together. What if robot can think of solutions for the problem by itself by looking at what is available inside? So this is fun emerging field that we can look at and see how it works. All this thing. So I think here the robot develops a tool for itself and finds a solution to the problem. So this is something that we can.
Voice.
There's no volume.
Can you put the link on in the chat?
Stress that humans encounter in these situations, they can come up with interesting solutions that might work and
we
make
can
this
also.
very long.
Mine was on mute. Not here.
Hi, is the video audible?
Just put the link. Chat. Not clearly.
Not clearly. Okay, I'll do one thing. I'll share the links. I think that is there in the. I don't know if I can improve this because it is playing on YouTube. I can share the link. It's called Tool MacGyvering. So yeah, I think it's there in the presentation. It's a PDF presentation, right? I'll do one thing. I'll share the entire presentation in its raw format so that you can check the links by yourself. Yeah. Apart from this, there are a few links that I've been looking at, some interesting project collaborative robots, on how robots work and how human machine collaboration works. So these are something that you can look at later dates, and how some projects that interest me. So that is something like that. Yeah, I think that is about it. This is the last slide. Oops. Okay, so there's a link out here. Oops. Oh yeah, okay. He shared the link. Diego has shared the link with everyone. All right. Thanks, Diego. I think that's a good one. So yeah, I think we've covered the theory aspect of it. Um, we'll switch to the Robot Studio tutorial now. But yeah, let's take a 5-minute break, and then we'll be back in 5 minutes and start with Robot Studio. And we'll look at the important parts of Robot Studio that we need to know. And then after that, we'll switch on to the Grasshopper code that we need to get into. Yeah. Oops. I'm gonna All right, we're back. I hope everyone's had a small break. Okay, before we proceed, I think Diego shared us a small video, and I'd like to share that. It's a very, it's quite an interesting video. Oh, 1 second, I'm going to, let's see what to share.
Download it first.
Yes, I have downloaded it. Share.
Share full screen. Oh, the entire.
I'm going to stop share and start a new share. Oh, for some reason I can't share the Windows Media Player.
So just share the entire.
Okay, one second. I'll just share my whole screen. Share screen. Okay, share. And can you all see the video? All right. Oh, this is an interesting Delta robot. Oh, it's pretty neat.
What's to make it 1 to 1 screen?
Yeah. So is it operating with the keyboard as you're moving this thing, or is it trying to, is it detecting the movement of the car and getting that?
My understanding is connected with the wheel,
Huh.
which he's playing, and then the game is giving that
It
feedback.
detect the physics in the video of the game. Oh, that's pretty awesome. That is pretty awesome. Yeah. Yeah, that is pretty good. I thought it was probably connected to the keyboard, but if it is connected to the physics of the game, that is pretty hard to do, I think. Yeah. All right. Thanks for sharing, Diego. That was really cool video. I yeah, I think that is the one of the main things, that trying to get one type of data, trying to find the APIs and the SDKs and try to integrate all the workflow through and through. That can be quite challenging. Right? So what did you use? Did you use OpenCV as some form of detection, or did you something else? Yeah. Okay. All right. I found different pieces of code from Arduino. Ah, okay. Yeah. Okay. Okay, here we have the ABB presentation. I'm going to switch on to my robot studio. 1 second. Stop share. Let me share my robot studio screen. Yeah. Okay, now y'all can see my robot studio. Just okay. So Robot Studio is a proprietary software that ABB has chips for its robot. Unfortunately, it's not a free software, and it is pretty expensive. And while we can use it for a month for trial purposes, you would need a subscription if you had to run the software. Any educational institutions?
Is there any open source?
No, unfortunately, there is no open source equivalent for the APP. But if you are in an educational institution, or if you are in an educational lab or an academic lab or a school or a college, then you can avail an educational license, which in some cases is free. I don't know, depending on where you are, it's quite free for us, but it can come at a nominal cost. So if anybody's interested, it's a good software to have. It some of the things like debugging the code or editing some of the startup processes can be done more efficiently in Robot Studio once you start to get more and more deep into the machine. But for our purposes, we will not be looking at the whole lot of things, but we will be looking at how we can see some portions of it. Some of the plugins often recommend, like for example, recommend running the G code in Robot Studio to check for collisions in case the plugin does not detect. So that is one of the reasons why it's good to have the Robot Studio. And for running the G code and testing the simulation, we do not need um, the paid version. We can do the free version. One of the sad parts about having the free version is you cannot save the files, or you cannot you can start an empty solution, but we cannot save the file. So saving is not an option. Anything that you do is temporary, and we will be able to do this. So I'm going to start with an empty station. I'm going to create a station out here, and so here, this is the whole menu bar. Here you have the this thing. If you want to, you can zoom in, zoom out. To press Control, Shift, and left click to go around the 3D orbit, to move it around the 3D. The third mouse button for scroll, and Control and left mouse button to pan across. So this is what you'll do. And here you have the main toolbar. Here you have home. You have the modeling bit. There's not a whole lot of modeling that we want to do in out here, and the modeling by itself is pretty limited. Or you have the simulation toolbar. Here you have the controller, and then you have the rapid code related functions out here, and add-in. So once you go into add-in, this is where your first small bit of editing the software that you need. You will have to download and install this robotware for IRC5. What it does is it helps you build a virtual controller into your Robot Studio, and you can try to create small programs. You can try to simulate the robot before you actually test it out on the robot. So all those, the virtual controller is quite an important thing when you want to play around, you want to study, you want to experiment with how some of the codes work, or some of the functional changes that you're doing works. So you can download and this thing. I have downloaded, I think, both 6.312. I think the latest 7 is limited apps, limited robots are functional on that. The other for the other this thing, you can use 6.13, which is the latest. I think both are available out here. You have 6.13 and you have, this shows only 6.13. Okay, this is the latest in this one. I think there is a 7 out here somewhere. Is that Omnicore then? Okay, maybe it is. Anyways, 6.0. Okay. So once you install this, you can install the package. I've installed it already. Again, you'll notice that I'm using the freeware as well. So whatever I can do out here, the same things you'll be able to perform in your this thing. If you want to import a library, if you want to check out the robots that we have, that you have in here, you have the model. This is a model that is available in our lab. So this is the 6620. It can take a payload of 150 kgs, and it has a reach of 2.2 meters. So this is the robot. So once I've added the robot, I can move it around. I can check out each of the arm. So I can move it around using this thing. This is a free hand movement I can do. Check out each of the axis. Here you go. It's the 4th axis, 5th, and 6th. Yeah. So this is just freehand movement that you can try out here. Here you can create an existing controller. Just going to delete this. Okay. I think if you will go into if you check my notes, towards the end, I have outlined how to create a virtual controller. So I have already created a virtual controller, but let us create a new controller just to show how it is done. Okay. So first thing is you install, once you've installed the Robot Studio apps, you go into this thing. Instead of, okay, so the 7 has only limited robots that you have, and this is not the robot model that I have in RobotWare 7. So RobotWare 6.310 is the ones that have the bulk of the robots. So I'm going to create another iteration of, let me try to create a different robot this time. Okay, 66700. This is again a robot that I had to work with. I'll try to create this one. Create import from library. Yes. 600. I'm just going to keep the name the same as it is. And okay, 1 second. Just going to check on controller. Start the one to controller the virtual device. Yes, rapid. Okay. All right, I'm just going to do that. Controller. Yeah. 6.13 6700. Also, I must mention that I'm running an older version of Robot Studio. Maybe your interface might be slightly different. If in case that is, then to let me know. I think this is Robot Studio 2021. The latest one, if you all are downloading right now, is going to be 2022. So I'm creating a new model. It is I think I think my notes is indicating a Robot Studio as 2022 installation manager. This takes some time to create. I'm going to select this one. All right, okay. We have a robot. Let's see. Here you go. So I have a robot out here and I have a controller. There's a controller active out here. So I can see all this, this thing. I have the rapid, I have the local IO, I have the configuration, and I have the home, this thing. I'm going back to the home to see plots and this thing. So in the layout, you can see the complete robot with all the links, each of the links. So I have this, the robot that I'm going to create. I have it out here. So again, I can, okay. If I click on this is something called linear jog. As I mentioned, linear motion. So this linear jog allows you to move along the X, Y, Z axis based on the world coordinate system. So here you have X. This is going along X axis. The X is red. This sorry, this is X. X is green. Y is no. This sorry. This is X. Sorry, this is Y. The green is Y. X is straight ahead, and blue is Z axis. Now here we see reorient motion. Now this is a very unique motion that you will come across in the robot, and all of this can be accessed to the flex pendant. I'll open the flex pendant in a second. What reorient does is, in case sometimes the robot is stuck, or if the arm is reaching singularity where it cannot bend anymore, then to get out of it, you can use the reorient. What reorient does is it keeps this point fixed, this point at the end of the sixth axis fixed, and it will start to rotate the arm around that point. It tries to rotate the arm around that point. That way it releases the arm from whatever singularity that it's trying to reach. So this is a very interesting motion. This point, at all point in space, it's going to be fixed, but its orientation might change, but its location in space in space will be fixed. Now I'm going to click on this robot and I'm going to go to modify, and I'm going to click on mechanism jog joint. Here I can see the complete reach of each complete motion of each and each independent arm. So this is the complete range of motion of the axis number 1 from minus 170 degrees to 170 degrees. This is the complete range of motion. Here you will see again at minus 65 to 85. This is more or less common for all the ABB robots that you see. One second, I'm just going to get this to normal. Here I have it from minus 300 to 300, and then here this thing. One thing that you will notice, I'm going to go to modify and move to pose. I'm going to jump to home. Now, one thing you'll notice out here is that, one second, I'm going to release that. You'll see that the axis number 5 is in 30 degrees. Now ABB robot has this unique thing. Every time this is in at 0, and whenever you try to jog along linear motion, the fact that these 3 axes are in a single line creates a small error, and this happens in the larger robot primarily, that when the 5th axis is in the same line as the 4th axis, when you're trying to jog it along the linear motion, it will create a small error that it's trying to it is reaching singularity in one of the axes, and it'll give an error in the flex pendant and refuse to move. So to avoid that error, what you do is just change the angle of this slightly, the 5th axis slightly, so that it can create an alternative path for it to go. This is only unique to the ABB robot, and particularly the large ABB robots. And I've seen this happen in the 6620 and in the 6700. So if you ever come across an error in an ABB robot where they, then please check out whether the axis is in the straight line. And if it is, just change the angle a little bit, and the robot will work fine when you're jogging. So, but yes, so here you have all the you can move the axis, and here you can again see the mechanism to linear jog. So you can jog the robot linear. So I'm going to type in 4000. Oops, okay, that is out of the reach then. 250. Yeah, straight. Y, I'm going to give 500. It's quite painful to click each this thing, but let's say 1500. It goes below. Yeah, and here RX, RY, RZ. This is the reorient motion. You're trying to I'm going to say minus 200. It changes the axis along that position. So yeah, this is here you can check out how to jog this thing. Now, one of the things that you will need to see is controller. Yeah, flex pendant. So this is the flex pendant. This is the exact simulation of the flex pendant that you're gonna come across in the when you're going to play with the robot. And this is the exact same interface that you're going to see out here. So you have the same buttons. Okay, you have the same joystick out here. You have these 4 buttons are to run the programs on. This is to switch between the axes. So I'm going to go to this is the menu bar, and you will see all these
mouse pointer.
What?
Can't see the pointer.
Can you see my mouse pointer? No,
but it's not moving now.
Oh, okay. Should I annotate? Okay.
Show it again.
Can you see my mouse pointer?
Yeah, but it's not moving.
One second. I'll do one thing. I'll annotate. No, annotate won't be good. Mouse. Yeah. What about now?
Are you annotating?
I'm not annotating. My mouse is my mouse on now?
Yeah, seems like.
Okay.
Shake. Yeah.
Okay. Sorry for that. So you go to the menu bar. You have the hot edit button, which is you have the input outputs. You have the jogging. I'm going to go to the jogging window. Here you will see all the parameters that you need to edit. If I was to click on this button, this shows that the joystick is programmed to run 1, 2, and 3 axes. I click on this button.
That's what I see.
Yeah.
Now we can't see any of those things. Show the entire screen.
Oh, I'm sorry. Give me a second. Give me a second. I think we're having a small problem out here. Can you see the?
No.
Oh, I'm so sorry. One second. One second. I am going to. I think the flex pendant opens in a new tab, and that is not being shown. I'm going to stop share, and I'm going to share my entire screen. Can you see the flex pendant now? Oh. That is very funny. Oh, okay. The virtual flex pendant is created on a different tab. Okay, I'm going to share screen share. Yeah, sorry, I'm so sorry about that. I didn't realize that the flex pendant opens on a new tab and this will not be visible. So again, I'm going to restart everything the same. So this is the flex pendant that you create. This is an exact replica of what you would see when you switch on the computer, when you switch on the robot. And so this is the main program window. This is the production window that you see out here. This is the production window. You can load a program from here, and then you can send and run or whatever you want. So this is the menu from here. You can load the program from here, but we're going to switch this off. So here you see this is the emergency stop button. Here is an enable button. Right now the motors are on. So and hold to run. So if you want to, this is just for simulation, but hold to run is for the dead man switch to activate out here. Yeah, and going back to the menu, you have the inputs and outputs, jogging, production window, program editor, program data. So we were at the jogging menu. This is the same jogging that you see out here. Now, these 4 buttons are to run the program, to stop the program, to proceed from one program to the next program. This thing. And here you will see the different within the jogging menu, you'll see all the different details of the robot. Here you have the which robot it is. It is not found, you cannot check it. And here you have the motion type. Now I can switch the motion type. And so when I click on this, I will see it's 1, 2, 3 axis. The moment I move the keys, move the joystick, I will isolate and move the first, second, and third axis. Whereas if I click it the second time, I will be able to move the 4th, 5th, and 6th axis out here. Similarly, this button activates the linear motion out here. See, and the motion is identified out here. And you can click again once again to create a scene. Now it become into reorient motion. So, and again, you can move it using the joystick to get out of whatever spaces out here. So here you have whatever tool that you've loaded out here will be indicated in this tool menu out here. The work object will be loaded out here. So these are the parameters that you can identify out here. The functionality is disabled as a robot controller is in automatic mode. Where is it in automatic mode? Okay. Can I change the automatic mode out here in this? Maybe not. Anyways, so, and then here you have the program editor. This is the area where in the flex pendant where you are allowed to write your own code using the flex pendant. It is not so much, we won't get into a lot of this, but since a lot of this modules are not active in this thing, but you can add an instruction out here, and you can add the instruction, and then you can try to you can teach the robot at a position, and then make the robot remember the location, and then create a path accordingly. So this is the this is basically the flex pendant. Here you have the this thing, what the main thing that I wanted to show in the robot tutorial is this inputs and outputs. This is where all the digital and analog inputs are set up in the in robot studio, or in the robot. And what it does is it allows you to send signals and receive signals from send signals to actuators and receive signals from sensors, which can be mounted onto the robot. This robot, depending on how it is set up, you can program the digital I/O to be activated by these 4 residual keys. So these 4 keys can be programmed to switch on and off the digital I/O as required. Okay, this is really slow, and I think it's gonna hang. Let me see. Okay. Quickly, there's a shortcut toolbar out here. Here you can manually control the speed of what you're jogging of your program. Here you can, this is the short and stop task. Here you have a single cycle, continuous cycle function out here. Single cycle, the program just starts and stops, and that's it. That's a single cycle. Continuous, it will restart the whole program again and again. We will keep it at a single cycle only. And the other thing here, you have an increment. This is not highlighted right now. That's mainly because when you're jogging using the joystick, each step is calculated. So if it is a small increment, it will take a small step. If it's a large increment, it will take a large step. While jogging, we usually keep it at none so that we can jog it at the highest speed that it's possible for us. So that is out here. Let me see if that DIO program data. All the data that is that we create, particularly the tool data, use data types. The main, particularly the work object data and the tool data that we embed. The work object coordinates, the tool coordinates, and the name of the tool and the work object are stored in this this area. By default, it is called tool 00. The next, when you create a new tool, it will be added out here, and this you can, and once you double click, you can see all the details out here. Here you will get the tool data that you're going to feed into your Grasshopper program. Namely, you will get the XYZ coordinates of the tool, and that is going to be fed along with the tool mesh to generate the tool. The other thing that you will require is the work object data. So this work object, since it's the default work object WOBJ0, it is the default work object which is defined by the robot coordinate system. It is not going to be of any value. But when you define a new work object, you will get the XYZ positions as well as the quaternion data. This will give us the position and the orientation of the work object. We will see how we can use this work object in the Grasshopper script that we're going to see in some time right now. Now, these two are the things that we need to collect from the robot flex pendant. So once we have these two data, we are good to move on to our Grasshopper script to do this. Okay, one second. How can I? All right. Sorry, I missed a small portion. So here you can see this button. This allows you to switch between the different types of modes that we have. Here you have a motors on mode, and I'm going to switch it to manual. Okay, now let's see all those functions that were disabled because of the motor being on automatic mode. Hopefully we'll be able to access them right now. What were we trying to access? Coordinate system. Yes. All right. The coordinate system, we have it is set on base. You can set it on world as well, and our tool. Tool. Okay. Now we're going to do a small exercise on how we can create a new tool, but uh, this would have to be attempted on the robot. I'll try to explain as best as I can without it being this. So tool, and I'm going to give it, we'll probably give it a different name. We're going to keep it as task. We're going to keep it as persistent, and we're just going to create, okay. If you want, you can keep it, yeah, task is fine. You can keep it global if you're going to use it tool across different programs. So we can keep that global, and we're going to create this thing. Once you created a new tool and it's in module 1, it's not in base, you're going to define the tool. You can change the value of the tool. You can change the declaration from what we did out here. We can change the value again, but before that we need to define the tool. You click on define, and you will try to, you will need to identify 4 points. As I said, and then starting on the earlier presentation, you'll identify a small point by positioning some sharp object, and you'll try to reach that point from different angles. And each time you reach a point, you're going to modify the position, and then you change the position of the robotic tooltip, and you try to reach it from a different point. Once you reach that point, you modify that position, and then you again reach it from a different point, you modify that position again. Like that, by using repeating that process, you're going to define, you're going to approach the point from four times, and you're going to reach as close to the tip as possible, and you're going to modify the position. Once you do that, you click OK. Okay. All right. I think this is mainly because we are not moving the robot. 1 second. Or maybe we don't have a tool on the robot. Let's see if I can. All right, I'm back. Let me see if this works. Modify. Okay. Anyways, I don't think this thing allows that. Let me see. That's a manual full speed. Let's try this again. Okay, I don't think we are able to define the position, but once you are to do this, you will be able to get the tool. And once you double click on the tool, okay, we can't access this. 1 second there. Yeah, and once you and here you will be able to see the coordinates of the TCP, and this is the TCP that you're going to get in it. Okay. Similarly, you will have to define the work object. Again, a new type of work object, preferably global. If you're going to use, if it's going to be the same work object that you're going to use it all across, maybe change it to global object 2. And in this process, you're going to edit. You're going to you're going to define this whole process, and you can either use the user method or you can use the object method. The difference is that in user method, it uses the user's coordinate system, whereas in the object method, I think it uses the global coordinate system. You will define 3 points on the object by taking the tooltip as close to the object as possible, and you're going to modify that position once you reach that position, and once you do that, you will get the coordinates of the work object, and you can view the coordinates by clicking on change value, or you can or in the jogging menu, and you will see the different positions, the different coordinates and the quaternion data. The q1, q2, q3, q4 are the quaternion data, and the xyz will be the coordinate data that is available to you. So once you have that, you can use that and transfer it onto your Grasshopper script. Okay, I'm just going to shut the flex bandit now. Okay, now we've had this robot that we've created out here. I'm going to switch this off, and we've created all of this components, but we've not moved anything. I'm just going to switch it back to home. Okay, here I've done. Now if I was to create a small script of how to move the robot in Robot Studio, how would I go about it? I would start by first defining a small empty path. So once I create the path, I have all this data generated, the tool data. Oh, before I forget, you have to add a tool out here. Now, tool library is something that is not available in the free format. So that is tough luck for us, but that's fine. We generally don't need that. We'll take it from the we'll load it in a Grasshopper script, and once we get the rapid code, that we'll try and simulate out here. So we have the path created. So now we are going to go back to okay, yeah. Now I'm going to go out here. I am going to teach this position. I'm going to keep this position as home, and I'm going to teach that position. Just say okay. I'm going to move it around here. Teach another position. Yes. Every time I click teach position, I'm creating a new target, and within the new move pattern, and at the end of the tip, I'm creating a new target. I'm going to move along this direction. Teach instruction. Yes. So here again, another teach instruction. Yes. Teach instruction. Yes. And lastly, go out here. Yeah. And teach instruction. Yes. Yeah. So I have all these targets created, and I can right click and view robot at target to see how it is moving. I can also click on the target and create move along path to try and simulate how the motion is going to look like. Yeah. Yeah. So okay, it is moving. Okay, this is here is how you can create a work object, but we will add our work object into our Grasshopper script only. So now that is done. Now we can where is configuration? What was the next step that we needed to take? Mm-hmm. Right click. Oh, sorry. Before, I think I forgot one important step before this thing. Sorry, before you set your targets, you need to adjust your speed and a zone, and define the tool out here and work object. So all these all these things that you need to change out, including move J. If you want to add a move do, you can add a, you need to define out here before you move that. So let me go through a couple of these things. What is the speed is the ABB speed. So you can define whatever speed it is in millimeters per second. And now zone is something that you need to that we need to understand. Fine is where whenever the robot is given a path, there are numerous points that you will define along the path. Now, around each point, you imagine a small ball of the radius of 0 mm, 1 mm, 5 mm, whatever. So when you're moving through the path, the moment you want to touch the point along the path, you would go to fine, or even fine. That means the robot's tool tip is going to touch that point and then move ahead. Z1 would mean that, imagine when it is close to up to 1 centimeter, when it reaches up to 1 centimeter of as close as 1 centimeter to the point, it will start to move in the other direction. So what this does is it helps you to move across the non-important points, like along the points along the path faster. So I was to create a zone 50 or a 500 or a zone 100. Imagine a ball, imagine a sphere of 50 mm dia around that point. And the moment the TCP touches the sphere around the point, it will start to move to the next point. Thereby, you don't have to actually touch the point along the path and then wait. So this is quite important. But when you're trying to mill, when all the important points where the tool has to touch, there the zone has to be fine. The rest of the points can be along zone 10, 20, or however you want the tool path to move. Zone, you can define the speed as per the limitations of your, as per the limits of your robot. Robots like 6700, they can move up to speeds of 2500 millimeters per second, 2500 millimeters. And yeah, you can define it at 100, whatever, on what speed you're comfortable with. If you're trying to mill, you would ideally keep the speed within the limits of what your drill bit recommends, what your spindle recommends, so that there is no breakage of it. Including, you will test out what speed works for you, or when you're moving it along, when you're trying to print, so that the print doesn't break. So this is within the range of what you're going to experiment with. Here, move J and move L is something that you would want to define. If you want to touch up, if you're trying to move along the straight line, it's best to use move L, and it will touch all the. And if you're trying to move along, move faster between points or between spaces, then you try to move J. Move do is, and move AO. This is, it starts. It gives it a digital output and does a joint movement. Move L do is gives a digital output and gives a linear motion, and then moves along the linear motions. Move A do, it gives an analog output and moves along does a joint, and does a move J or move joint motion. So similarly, you can choose which of this motion that you want. Mostly we will work with all these parameters we will define in our grasshopper code. So you have so once you've defined this, you move on to creating your targets and creating the simulation that you're going to see out here. Yeah. Okay. Okay. Okay, now I'm going to click this and rename it as main. Okay, so this main is the entry point into the code. Now all yeah um uh, so I'll explain this and get back to the structure of the rapid code. So this main is the entry point into this code. So once you've created the main, and you're going to right click and insert move action, right click. One second, main. Insert procedure call. Oops. Huh, I can't insert a procedure call. Okay, I'm going to, instead of main, I'm going to start as a simulation entry point. And synchronized. Okay. 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 Go to declaration. Yeah. Main. Okay. Module. Simulation. Hold on 1 second. Paths and targets. Main. Nice to rapid insert. Choose path and insert. Proc and proc is there and proc is there module. Yeah, this is fine. Main is there. Okay, that seemed to be an error. I think I made a mistake somewhere. Insert procedure call is not active. Okay, view at target is active. 1 second. So that is all right. So I think there is some error happened, because of which I'm not able to insert a procedure call, and then try to simulate it. That was the last bit of this thing. I will check what went wrong with this program, and then we will rectify it. But until then, let's continue with this thing, because this was the only thing that I wanted to show in the Robot Studio before we started to switch on to our Grasshopper scripts. Um, 1 second, I'm just gonna minimize this. So yes, and this is where once you simulate that, you would get the rapid script happening out here. So this is that would create the rapid code that you can uh, copy it and send it into the robot, which can be then printed, which can be then simulated, or actually send it to the actual robot for this thing via USB, or you can directly connect it. If you want to directly connect Robot Studio into your this thing, you can go to your controller and add a controller. So you can do a one-click connect by connecting it to the external port of the controller that I showed on 1 second. Yeah. Yeah, you can connect it this service port and then click on one-click connect to the Robot Studio, and you will be able to connect it. Once you have it, and you will have to request access. Once you have that, you will get this request access will get highlighted. You can request access and then send the program directly by checking program and program counter start. You can send the program directly to your robot to operate it. Yeah, but it's best to run the simulation first and then check it out. All right. Now, I think what is the time? Do we need? Does anybody require? Do we need to take a break and before we come back and sit on the Grasshopper code, or should we continue along? What am I sharing? Nothing. Okay. Okay. I think if you all will check in the files that I uploaded, there are few files that I have, namely milling files. 1 second. Okay. There are a few files that I was looking at, namely the move. 1 second. What are the files that I uploaded? Let's
Move robot, move component, 3D printing and well.
yeah, move robot components and another thing. I'll start with move robot first. This is yeah, digital features. Move robot, yeah. So this was the file that I selected. I think we can try to create a small script ourselves. I'm just going to start from scratch. But you feel free to refer to this thing. Couple of things we will take from this script is the robot settings and the files that we need to look at. Yeah. So I'm going to take a new this thing. I'm just going to put a bifocal stab out here so that you all can see what this thing is. And I'm going to open this thing and I'm going to put in a curve out here. Let's put a NURBS curve. Yeah, this is a curve that I've put out here. I'm just going to put a curve component set one curve. Yes, so this curve I have a curve set out here, and reference planar curve. I'm just going to divide this curve into as many points. I can maybe increase 10 to maybe 30 points if required. Okay, maybe that's too many. Let's keep it at 20. Yeah. Now, the easiest way to go about it is just put an XY plane and then you have the planes along which you go out here. This is it. These are the frames. You need to send in your frames to the robot that you need to go. But one of the main things is how does the robot approach it and then go out there. So that is something that we decided. First, let's set up our robot as well. This is the robots plugin, but let us first define the robot components plugin. Let's see what we have out here. We have our let's see what else. So this is a plugin. Here we have all the components for joint target. We will need a joint target component. We will also need a robot target component. These two things we are going to use. We are going to use what else are we going to use? Rapid generator. Yeah, that will use. Then we are going to add. Okay, the remote connection we are not going to get plain deconstruct. No definitions. Yes, let us select our robot first. I'm going to select the robot that we have 66620. This is the robot that we have. Yeah, I'm gonna position it to have. Okay, now we need to mount the external the tool that is required. So I'm just going to copy the tool that I've already created out here. That is the geometry tool that I have. Just going to copy. I'm going to paste it out here. Oops, there is my tool. Here, I've already referenced the tool out here. I've just built a small mill. This thing takes in a mesh. So you need to convert it into a mesh. And then you're going to send this into the robot axis. Oh, sorry. Oops. X. Perhaps I should shut down some of the unnecessary tools so that my Rhino doesn't hang. Sorry, I sent the wrong component into it. Never work in haste. I need the robot tool definition from here. Yeah. This is what I need. I can put the mesh in out here Here I'm going to give it a name, maybe tool 1. The second give. And what else do I need? I need to define the attachment plane. Now the attachment plane is it's going to be this point. So I'm just going to I'm just going to bake this out here. Going to shade it. I want to attach it at this junction. So I'm just going to create a point out here. And I'm going to insert a point. Set one point. Define this point out here. So this is the point where my tool is going to connect the sixth, the end flange. So once I got that, I will create a frame. I'm going to say, I don't know what it should I rotate X? I need to rotate it this way. So instead of XY, I will shoot a YZ plane. No, wait, I need to, okay, but then no, it has to be an XY. I'm also going to create a flip plane so that I can orient it in whatever direction I want. Later way, green toggle. Oops. And this I've got the attachment. Now I need the TCP. If my model is accurate, I can take the end tip, but it's best to define the TCP from what you get from the Robot Studio. So for time being, let me take the TCP from the model just for simulation's sake, and then we'll change the thing. I'm going to copy the same thing out here. Just going to define that at one point. Yeah, just going to internalize this. Internalize the data so I can delete the. I'm going to mount this onto that, and here the robot tool is attached to it. Has the okay. This is the issue that I was facing. Now this has rotated. Now I need to rotate this the other way down. The TCP is in the wrong direction. Yeah. XY. Can I make it flip? Oh, okay. I need to rotate that flip plane is this is a tool plane. Yeah, now I've oriented in the right direction. So it's always best to have the flip planes so that you can orient it in the direction that you want. There you go. And now one of the things that I'm going to have to check when I'm simulating is whether this plane is pointed in the right direction or it's going in some other direction. So here this is currently by default position at 0, 0, 0. Now, oops. Oh, okay. I'm going to position this in the direction of the robot so that it can go up here. Just going to position it out here. Now from here, I'm going to set the robot target. I am again going to copy all of this once because I'm pretty sure I will need to rotate. Okay, I might not need to rotate the plane. So this will go here. I'm going to go into plane axis configuration. No, wait. No. Before I get into this, I will need to get speed data move override robot tool. Robot tool calibration 49 to plane. Zip plane X. Second. I will an external joint position zone data. 1 second. Target and move. Yeah. Okay, yeah. So oops. This will go out here. Here you can give it you will give okay. Speed data is gonna be override both object override distances. This you can okay, one second. I'm gonna reduce the speed. Drop down the 1 second. Edit. So this is I'm gonna get this as 100, 200, 500. Okay. Something like that. Okay. I guess I should just change the name to V100, V200, V500. I'll add a V50 also. V50, go to 50. Okay, 50. Zone data is all right. What else is there? Absolute joint moment. Let's combine. I'm going to go joint movement. Oh, sorry, I'm going to go linear motion. All right. So this is there. Now, what do I require? I require a kinematic solver. Path planner. Where is my path? This is what I can get my definitions. Where is my path planner? Nothing. All right, yeah, here's a path generator. I'm going to send in my action. I'm going to send in my robot. Put a button out here. All right, so there is an error. Yes. What is the error? Robot 5th, the movement. So the position of the robot axis 5 is not in range. The first error we can solve. The second axis is a more problematic error. The second error, that's 5 is not in range. And if we look at the simulation, we will see why it is crashing into this thing, because I think it's mainly because of the TCP that we've defined, and it is going along the wrong axis. So this TCP is something that we'll have to redefine. I think the plane that we've taken is wrong. Let's take a X, no, yeah, X, Z. Yeah, okay, now the error is gone, but we are milling it in a very odd direction. We need it to be vertical. So we created the path, but we needed to mill it from the top. Let's see if we can achieve that. No, that was a bad decision. Let's call this, let's bring this out here so that we can take a look at this. Hmm. Should it not be XZ? Should it be YZ? Okay, I think we are at the wrong way. It has to be XY only. But XZ, it's YZ. Let me see this plane. Yeah, this is it. So yes, I made a mistake out here. So a lot of this is a mistake that happens, is all too common with me. When I try to create a plane, I forget, I don't know which is the orientation of the TCP, and you end up creating a very weird path from a very, this is the right angle that you can create. The tool is going properly. Now you created this tool and you've gotten the path out, but then you see the small error. The first movement is not an absolute joint. That is an error that usually happens because ideally the first motion, the robot should take the fastest path to the first position. So it is always ideal to keep it a movement J so that it can orient itself and then come to this position. So how do we go about doing that? One thing is, what we can do is we can create a joint motion, which is an absolute path, which is at the home point, and so that wherever the robot is, it will go as an absolute path to that point, and then go down into the go down to the code and start printing. And also, so let us start create a joint. Let's create a joint movement. How do we do that? I will create a robot joint position. Okay, this is the robot joint position. I will need to connect this to a joint target. This is the joint target that I'm going to require, and I'm going to require a move function here. Same this thing. I'm going to copy and paste it out here. Is there a separate move target for joint? What is the error? Joint target cannot be combined with, okay, yes, it will have to be absolute J. Yes, now you see the error is gone. Now, the robot position that we require, I think in Robot Studio, we had set up the position as 0, 0, 0, 0, 0, and then the fifth axis was 30 degrees. So I'm going to create all that positions out here, because this is going to be the home position where all the axes are at rest. Sorry, this one. This is going to be 0, 0, 0, 0, and 30. Not creating that singularity situation. There you go. This is it, and that's going in absolute joint position. From here, it is going down to after it from wherever the position is located, it's going to go home first, and that's going to be an absolute joint motion. It's going to go there the fastest and the way possible. And once it's done that, it's going to go down to the position where we need to move along the path. And then after that is completed, it is again going to go into the, it is again going to go back home. So I'm going to merge these parts. So I'll start with this. Then I'm going to go this one. And again, it has to go back. So each of this, I'm just going to flatten it as I enter. And here I send the action. There you go. Once I updated the new paths, you can see that the error is gone, because the robot is happy that the first position is an absolute J position. So how the pathing works is, it starts on the home position. It goes to the fastest. It goes as a move L position. No, sorry, it goes as a move L position to this first point. It moves along this path along a move L position, and then it goes like a move absolute J to this to back home. Now, all this is fine. One of the things that I would urge anybody who's milling is that let it go close to the robot at a J motion, which is a fast motion. Then from a point which is above the milling or the printing area, let it go as a move L position to the final to the first actual point where the operation has to be done. So that what it would do is that it will so that the robot can move really fast up until that point and then slow down to the speed that it requires to it, rather than starting real slow as a move L position from the absolute J position, rather than starting the L motion from this point all the way to the geometry, to the curve, and then moving it along this curve. What we can do is we can create a small offset where to which the robot will first reach in a speed which is determined by us, a faster speed that is determined by us, and then slow down and gradually move down to the milling or the printing or the move along path for it. How can we achieve that? So we've got these points. I'm just going to create endpoints. I'm just going to get the endpoints of the curve. So I've got the endpoints of the curve. I am just going to move that along the Z direction. Give it some distance of say 100, so that this point can be reached by the geometry. And I'm going to repeat all of this. Oops. And we're going to need another point out here. Flatten it. Now this I'm going to increase the speed a little bit, maybe 200. And from here again, hold on 1 second. This, okay. I'm going to dispatch this because the first point is going to be, oops. Yes. So it has to reach this point, then go down, and here I'm going to create another position for the last point. Again, flatten this. Yeah, and directly feed back into there. So now the new tool path is it's going to, okay, and now we're going to change as absolute J. This is going to be a move J. So it is going to be a joint motion. And now if we look at the tool path, the tool goes the fastest position to this offset point, then it gradually goes down onto the tool path that it needs to take. It goes along the tool path, goes up, and then takes the fastest route back to the home position. Right? Absolute change, this, and yeah. And 1 second, I'm going to create the code generator. Where is the, yeah, the rapid generator. I'm going to add the update out here. I'm going to add the robot to this. I'm going to add the action out here. So this is the final G code that is being generated by the this is this what we see in the program module is what is going to go out here. So the first movement is absolute J, and it's going to the home position. From there, it's a movement J to the offset position, and then it goes all the way move L until it reaches the second last position, which is again it's going to be a move J to the top position. I think I think it would be best if we can use this also as move L. Sorry, this also as move L. Yeah, because you want to move straight out. If there is slight variation in that, that wouldn't benefit. So yes, move L is actually quite beneficial. And then towards the end, the first and the last movements are going to be move J. The only other move J that I can think of should happen is from the home position to the first point. That is what, all right, yes. So I can do one thing from here. I can dispatch. I'm going to remove this dispatch. I'm going to delete this. I am going to add this out here. Sure. Button this. And only the first point is going to go as the plane into this thing. So I got only a move J position at the first point. Now, did I do the other way? Oh, okay, 1 second. Move J. Update. Yeah. So I got a move J position from the tool path. From here, I'm going at a move J position. Oops. I think I changed the order of the pointless. 1 second. I mean, this is a better thing to attempt. Yeah. Let us see. Maybe it'll take care of the error. Or is this the other? Okay, I think I've messed up the order of the points. Which is the first one? Oh. Open that one. This is the first one. This should go down here. Okay, so this first 2 points are exactly correct. Now this. Okay, my bad. I have. This should be here. I'm sorry for that mistake. Yeah, there you go. Gotcha. Okay, this is a move J position, but it's still last movement is move J. This is move J. That's not move J. Oops. Yeah, I am clumsy. Yeah, there you go. This is what I've been trying to achieve. I've been repeatedly failing at achieving. So it the robot reaches home position and absolute J. Then it takes a move J position, which is the fastest motion, till this first point out here. From there, it takes a linear motion all the way till this point, and then it exits out at a linear motion. And then lastly, it takes an absolute J position back to this thing. So if you can see here, absolute J, the movement J, all the way till L, and then an absolute J. So this code is quite accurate, and you can see the speed data varying. It starts at a 200 speed, and all the way it goes back to 50 speed, and then lastly, so this is again 50 speed. So we can put this to maybe 200. Yes, this is also perfectly fine, and update it. Yes, it'll go back at the home position at the right speed. Everything is zone 0. We would prefer this thing to be fine. What does this take? But zone 0 is also fine. Toolpath TCP, yes. 0, 1, okay. Movement type integer speed data, yes. So there you have the first code, which is for moving in the path. And this is the right way to go about it. Always define the home, always define your offset points, and always define the return to home position to get into it. So, yes. All right. I am. So we have crossed our hours. So I think we have fallen short of one exercise that we plan to do. What is the 3D printing exercise? I think I can quickly discuss that thing. We'll run through the code. We will not we will not uh, do a live coding situation, but let's give it a quick rush through, like a 2-minute yeah. Okay. 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 Quickly, I'm just going to define the blocks. Here, this is where I've defined this whole block is where I've defined the geometry. You all can think of any better geometry, then it would be much nicer. This is what I did, what I could do first. I got the points. I pushed up points and defined the frames out here. Here I defined all the complete robot position, the tools, the TCP, the same as this thing. But here I've defined the work object from the point that I got from the quaternion data and the XYZ data, coordinate data that we can get from the flex pendant. So on the 4 quaternion data and the XYZ data defined, I got into a plane, and that I got into as a work object, and that I put it into the robotic work object data. Okay, so you can write and add the robotic work object data as well. Here I did the same thing. First is the home position, absolute J, and then all the move L positions, and then finally lastly another absolute J back to home. But this time it's going to print on the work object. So I would suggest everybody just have a look at this code, study this code, and maybe tomorrow first thing in the morning we'll discuss this code. First thing at the start of the class we'll discuss this code before we go on to milling and the other this thing. If anybody wants to, I think I have shared the milling code as well. Have a look at it. We will look at the rules to go about in the milling. It is pretty same. It is pretty similar to the code, the move robot code. You always have to have offset because you have to mill this and then you have to optimize it by reversing. There's one tricky component which is to reverse the pathways and to mill along the line. But once you've got that sorted, I think it is more than enough to continue with the code. Yeah. So I think we can stop today. Does anybody have any questions? Or I think everybody can try this out, check the code, and maybe if there is any questions, we can discuss it tomorrow in the morning. All right. Okay, Diego is saying all clear. All right, sounds good. Okay, so we'll pick it off from where we ended out here, and we'll again check that error. I'll see what that error is in Robot Studio and maybe sort that out. And we'll pick up on this thing. And once we check this out, we'll check out the other plugin also, the Robots Plus plugin. And we'll check out Machina also. That is a very that's quite a cool plugin that allows us to communicate real time with the robot. So we'll have a look at that also. But there are tutorials for both the plugins online. Just if you get time, just have a look at it. It'd be great to go through it. All right. Anyways, we'll see you guys tomorrow. All right. See you. Bye.